Here is a question where you are supposed to spot the mistake in the student's working. The student has concluded that ABC, triangle ABC equal to similar to triangle DEF because there is a side similarity test. The mistake here is that for SSS, it is actually a test for congruence test and not a similar test. So even though they are similar, because they are congruence, this is actually a congruent test and not a similar test. And let's do another quick test. If you have a triangle, PQR of sides PQ equal to 3 cm, QI equal to 4 cm, PI equal to 5 cm, triangle XYZ has sides XY equal to 6 cm, YZ equal to 8 cm, XZ equal to 10 cm. You will ask whether these two triangles are congruent, similar, or neither. How will you approach this problem? First, we can start the testing for congruency test. You know, for triangle the congruence, all the sides must be equal. And obviously, looking at the measurement, 3 does not equal to 6, 4 does not equal to 8, and 5 does not equal to 9. Since none of the sides are equal, these triangles are definitely not congruent. Now, the next thing we could do is to test for similar tests. For similar tests, the side must be proportional with the same ratio. We can check that PQ to XY equal to 3 over 6 equal to half. QR to YZ equal to 4 over 8, which is half. And lastly, PR to XZ equal to 5 over 9, which unfortunately is not equal to half. Therefore, our answer is that these two triangles are not congruent and they're also not similar. So this helps us illustrate an important point. Sometimes they might look similar or they might share some proportionate relationship. You might think they are similar. This is not true all the time. All the corresponding sides must maintain the same proportionate relationship for the similarity to exist. And try to have a systematic approach. You can check for congruence test first, and then you check for similarity test. This can help you avoid making assumptions and ensure that you reach the correct conclusion. Well, here's another problem. You have a triangle ABC and you are told that point D lies on BC with BD to DC have a ratio of 2:3. The line through D parallel to AC meets AB and E. Prove that triangle ABC is similar to triangle EBD. The best way to deal with this problem is to try to draw this triangle. First, we know the triangle is triangle ABC, and then point D lies on line BC. We know that point D lies on BC with BD to DC to 2:3. And then we are told that there's a line through D parallel to AC that meets AB and E. We notice that they have a common angle. Angle ABC is the same as angle EBD. And since ED is parallel to AC, angle BED is also equal to angle BAC. They are the corresponding angles. So, given that we have two equal angles, we know the third angle is the same. And therefore, angle ABC is similar to angle EBD by the AA rule. There's something interesting you can observe from here. When the line is drawn parallel to one side of the triangle, it will create a smaller triangle that is always similar to the original triangle. You look at this example. Since ED is parallel to AC, we can use the property of a parallel line that is cut by a transversal. When parallel lines are cut by a transversal, the corresponding angles are the same. Therefore, angle BED equal to angle BAC, and similar angle EDB equal to angle ACB. Both triangles also share an angle B as a common angle. Since the three angles are the same, we conclude that these two triangles are similar. Let's do something interesting to see how this can apply in everyday life. We can try to see how to use shadow to measure height. This is similar to how ancient mathematicians used to measure the height of pyramids. The problem tells us that at a certain time of the day, a 2-meter tall lamppost creates a 1.5-meter shadow, whereas a nearby tree casts a 12-meter shadow at the same time. If you assume that both objects are casting the shadow simultaneously, the sun's angle should be identical for both, creating similar right triangles. Let's try to visualize this. An object and its shadow form a right triangle with the ground. The lamppost triangle has a height of 2 meters and a base of 1.5 meters, whereas the tree triangle has an unknown height of x and a base of 12 meters. Once you draw the diagram like this, and then you let the height of x be x centimeter, since both lamppost and tree are similar, you can put the x divided by 2 is equal to 12 over 1.5. And then you can conclude that x equal to 16. So without measuring the height of the tree, you can know that the height of the tree is 16 meters long just by measuring the height of the shadow. Here, you can clearly see how we are using this in a real-life situation.
Smash your maths exams. Download Learn Maths Today for real exam questions and achieve top marks.